Okay, let's dive into this. Welcome to today's Explainer, where we're going to tackle a genuinely fascinating problem in the world of artificial intelligence. Basically, we're asking, how exactly do machines plan for chaos? You see, in a perfectly predictable, sterile world, AI has a really easy job. But the real world? Well, the real world is messy, it's unpredictable, and frankly, it rarely goes exactly according to plan. This right here is the single biggest hurdle separating the hyper-competent AI we see in science fiction movies from the real-world AI that sometimes gets stuck just spinning in endless circles in the corner of your living room. Today, we are going to thoroughly break down how artificial intelligence systems actually navigate this real-world uncertainty using a brilliant, albeit complex concept known as the and/or search in non-deterministic environments. By the end of this, we'll explore exactly how a computer thinks when the universe inevitably throws a wrench in its gears.
So here is our roadmap for this explainer. First up, we'll look at when perfect plans fail, establishing the core problem. Then we'll map out the actual solution in the and/or search tree. Third, we're going to outline defining a winning strategy. Fourth, we'll apply all this theory to a highly relatable scenario we're calling the slippery vacuum world. And finally, we will figure out how to avoid getting stuck forever in escaping the infinite loop. Let's jump right in.
Section 1. When perfect plans fail. Because, let's be totally honest with ourselves, they almost always do.
Now, I want you to imagine an AI agent for a second. Let's use a super relatable example, like a robotic vacuum cleaner operating right there in your living room. It boots up, it scans the room, and it computes this mathematically perfect, highly efficient route to clean your entire floor. It calculates the exact distance, the exact torque needed for its little wheels, and it confidently executes the very first maneuver. And it immediately gets stuck on the fringe of an area rug. Or maybe its wheels slip on a slightly wet patch of hardwood. So what happens when a robot's perfect plan goes perfectly wrong? Well, think about the last time your own smart device did something incredibly dumb just because the real world didn't perfectly match its internal map. If the AI doesn't have a backup plan, it completely freezes up. It just stops, and a frozen robot is quite literally a useless robot.
This brings us to an absolutely core concept in computer science. It's called non-deterministic environments. Now that sounds like a fancy academic term, but it really just describes a space where the transition model is not perfectly predictable. So what does that actually mean for our little robot vacuum? It means that when the agent takes an action, it cannot be 100% certain of the result. Our robot vacuum might try its hardest to move forward, but occasionally, maybe 1 out of 10 times, it just fails to move at all. Or maybe it tries to suck up a dust bunny, and instead, its exhaust accidentally flings dirt into a square it literally just finished cleaning. Because the environment is non-deterministic, because it doesn't play strictly by the rules, a simple, rigid sequence of step-by-step actions is completely useless. It falls apart at the first sign of trouble.
So because the AI absolutely cannot rely on a single, rigid sequence of actions, it has to adapt. It must use what we call a contingency plan, or a strategy. This isn't just a plan B. A true strategy in this context is a plan that specifies exactly what to do for every single possible outcome the environment might present. The agent has to stop thinking linearly, like, I will do A, then B, then C. Instead, it must start thinking entirely in terms of what-ifs. It has to say, okay, if I try action A and the environment responds with X, then I will do B. But wait, if the environment responds with Y instead, then I will do C. It's a fundamental, massive shift in how the machine processes its future. It's honestly an exponential leap in difficulty, forcing the AI to transition from thinking in a straightforward one-dimensional line to calculating a massive three-dimensional web of possibilities.
Moving on to Section 2, the and/or search tree. Let's look at how we actually map out these choices.
Now, what's really interesting about this slide and this concept as a whole is how we reframe the entire problem. To find these complex contingency plans, we have to dramatically expand our standard search tree. We aren't just mapping out the agent's choices anymore, we are expanding the entire tree to include the environment's choices. Think about the environment almost like a rival player sitting across from you at a chessboard. Programmers literally have to code the universe as a hostile, or at the very least, indifferent opponent. The AI makes a move, and then the environment gets a turn to respond, often in totally unpredictable ways. To win this game, the AI has to mathematically map out its own moves, plus every possible chaotic move the environment could make in return. It's kind of mind-blowing when you think about the scale of it.
Let's break down the actual anatomy of this new expanded tree. As we can see in the comparison here, we have two distinct types of nodes. First up, the OR nodes. Think of these as the agent's deliberate, calculated choices. At an OR node, the AI agent confidently decides, I will choose one action from these several possibilities. It chooses this action or that action. It's in control. Simple, right? But then we hit the AND nodes. This represents the chaotic, non-deterministic response of the environment. The AI doesn't get to choose anything here. The environment completely dictates the outcome. The environment might give the AI the exact result it wanted, and it might simultaneously give it a result it absolutely didn't want.
Let's look at a highly specific example of an AND node to really cement this. The agent is at an OR node and decides to take an action, suck up the dirt. Great. Now, because the very next step is an AND node controlled by our unpredictable environment, the AI must account for multiple realities splitting off from this single simple action. The result might be state A, which is cleaned, excellent, job well done. But the result might also be state B, still dirty, maybe because the vacuum's motor stuttered or the dirt was stuck. The AI doesn't get to pick state A or state B. So why on earth is it called an AND node? Because the AI must formulate a rock-solid plan for state A and state B branches coming out of this node if it wants to absolutely guarantee success. It literally has to cover all the bases.
Which brings us to Section 3, defining a winning strategy. How do we actually know when the AI has definitively solved the problem?
In a standard, completely predictable deterministic world, the easy world, a solution is just a straight line from start to finish. It's a simple, elegant, singular path. Just follow the line and you win. But as we've established, in a non-deterministic world, a straight line won't save you if the environment abruptly pushes you off that path. So a true solution transforms from a simple line into a vast, branching subtree. It's an entire sprawling web of if this, then that scenarios. You need the whole tree, not just a single branch, to ensure you can reach your goal no matter how the environment decides to react.
So the crucial point is that a winning, foolproof strategy must strictly adhere to 3 specific characteristics. Let's walk through them carefully because this is where the math gets rigid. First, the subtree must have a goal state at every single leaf node, meaning no matter which crazy chaotic path the environment forces you down, you eventually reach the finish line. Second, it specifies exactly one action for every OR node it encounters. The AI can't be indecisive. It must always know exactly what it chooses to do when it's its turn. And third, and guys, this is the really big one, it includes every outgoing edge for every AND node it encounters. The gravity of this cannot be overstated. You absolutely cannot ignore a possible outcome just because it's highly unlikely. If there is even a tiny 1% chance of a wheel slipping and the AI ignores it to save computing power, the entire mathematical proof of the strategy is instantly invalidated. Every single trick the environment could possibly pull must have a calculated response ready to go.
Section 4. The slippery vacuum world. Let's take all this abstract logic and see it in action.
Imagine our robot vacuum again, but let's put it in a world where the floor is incredibly slippery, freshly waxed hardwood. Sometimes the straightforward move action simply fails and the agent just spins its little wheels and stays exactly where it is. So the agent is sitting at its initial OR node and confidently decides to move right. But boom, we immediately hit an AND node. The environment responds as our opponent. The environment can result in 2 totally distinct states here. It might result in square B, which is a success, the vacuum successfully moved, or the environment might result in square A, complete failure, slippage, the vacuum is stuck in the exact same spot it started in.
Now, to have a valid mathematical solution here, the AI must deploy a specific contingency plan. It has to map out both of these realities. The solution specifies, okay, if the result is square B, great, I'm going to execute the action suck and clean the floor. But it also strictly specifies, if the result is square A because of slippage, the next action is to try moving right again. The elegance of this is actually really striking. The AI doesn't experience surprise or panic when it slips because that failure was already fully baked into the math before it even moved. Humans rarely plan this way, right? We don't usually map out every microscopic failure before walking across a living room. But the AI must. It just references its massive contingency tree and fires off the next appropriate action without missing a beat.
Section 5. Escaping the infinite loop. What happens when things just keep going wrong?
Let's move to this next concept and see how this builds our understanding of what are called cyclic solutions. A cycle is created when an action leads right back to the very same state in the search tree. So back to our slippery vacuum example. The vacuum is in square A. It tries to move right. It slips, and it stays in square A. Its perfectly calculated contingency plan says, try moving right again, so it tries, and it slips again, and it stays in square A. Suddenly, we aren't just moving steadily down a branch of a tree anymore. We are caught in a loop, endlessly circling back to the exact same node. Now, in computer science, an infinite loop is a massive system-crashing danger. If a program gets permanently stuck looping the same command, it freezes entirely, making this a truly high-stakes problem for our AI. When facing these frustrating cycles, the AI's internal logic often sounds something like this little nested rule. Do action X, if the result is Y, do Z, otherwise repeat X. It's actually quite playful when you think about it. It's literally the internal monologue of a highly persistent, maybe slightly frustrated machine. I'm going to try to move right. If I end up in the next square, I'll clean it. Otherwise, I'm just going to keep trying to move right over and over and over until it finally works. This classic if-then-else logic is the agent's primary mental weapon against the chaos of the cycle.
But here is the absolutely critical rule regarding termination. Getting stuck in a loop isn't necessarily a failure of the algorithm. It happens. However, a cyclic solution is only considered a mathematically valid solution if the agent is strictly guaranteed to eventually break out of that loop and reach the goal. The logic is allowed to loop, sure, but it absolutely cannot loop infinitely. The math behind the search tree must definitively prove that the cycle will eventually terminate, and the vacuum will eventually break traction and finish the job.
And this brilliantly illustrates a deeply fascinating philosophical point built right into the hard math. The AI's cyclic solution is valid, assuming the environment doesn't actively conspire to keep the agent in a loop forever. We literally have to assume the universe isn't actively and endlessly conspiring against our little robot. AI relies heavily on the laws of probability here. Eventually, that wheel simply must catch traction. If the world is 100% hostile 100% of the time, well, no intelligence, artificial or human, can ever succeed. But as long as there is even a microscopic fractional chance of success, the AI will just keep looping its contingency plan until it finally wins the game.
So, this leaves us with a pretty wild thought. If an AI must build out this massive, unbelievably complex, branching tree of AND nodes and OR nodes and contingency loops, just to vacuum a mildly slippery rug in your living room, how on earth does it plan for the truly infinite chaos of the real human world? Think about self-driving cars navigating heavily congested city streets in the rain, or robotic surgeons dealing with totally unpredictable human anatomy. The sheer scale and depth of the and/or trees required to navigate our realities safely is just staggering. It's a real testament to the incredible power of modern computer science, and it shows you just how much exhaustive planning goes into even the simplest artificial decisions. Thanks for joining me on this deep dive today, and keep asking those big questions.